The exercise says that the design flow can assume values only for 3 values. And these values are 80, 100, or 120 liters per second. And of course, this is a situation which is not really realistic, because usually the design flow is a real variable which can vary continuously within a specified range. Usually it doesn't assume fixed values. This is a situation that was adopted here in order to simplify the computation. Okay? But usually, unless you have some specific, only some specific machines, turbines that you can use, which may imply that the design flow can assume only specified values, like in this case. Unless you are in a similar situation, usually you have a turbine that can be sized, designed to allow you to cover any real value for the design flow within a specified range. But again, this is a situation that I adopted because for simplicity. So basically, you have only these 3 alternatives. So you have to select among 80, 100, or 120. And then the exercise says that the utility functions, and I will specify you what is a utility function in a moment, the utility function associated to the above indicators, depending on the design water withdrawal, design flow, are reported in the following tables. And you see 4 tables which gives to you the value of what is called utility, which varies from 0 and 1 for each design flow. So what is a utility function? The utility function is generally adopted in decision theory to give a score to each alternative with respect to a specified criteria. Again, the utility function is used in decision theory to give a score to each alternative decision with respect to a specified criteria. Basically, the utility function tells you how alternative decisions performs with respect to a criteria. This is what a utility function tells you. And you may say, I don't need it, because, for instance, the economical benefit. Why should we need a utility function? Because, the score of each alternative with respect to the criteria economical benefit could be given by the economical benefit itself. You perform a cost-benefit analysis for each alternative design flow, and then you end up with a net benefit for each of the alternative decisions. And this is the score with respect to this criteria of your alternatives. So you may say, I don't need it. That's true. But when you have more than one criteria, for instance, and you have to compare decisions, alternative decisions, against different criteria, it may be useful to give a score which is adimensional and is included for each of the criteria in the range 0, 1. So it may be useful if you convert your economical benefit given by each design flow in a score that varies between 0 and 1. Because in this way, it is more easily comparable with the scores that you get in the other criteria. Because when you talk about impact on the landscape, how would you measure it? It's difficult to measure it. You have to adopt a measure, and in this case, the measure is a utility function. So you basically, for each decision, you measure the impact on the landscape within a range 0, 1. Of course, in this case, the measurement is a bit subjective. For the case of the economical benefit, it's more objective. Because the economical benefit is measurable. The impact of the landscape cannot be measured by definition. It's a trick that you adopt to measure it through the utility. But you can easily understand when you have to compare these two criteria, impact on the landscape and economical benefit, that it may be useful for you if alternative decisions were ranked against each criteria in the range 0, 1. So this is why utility functions are used in decision theory. And you already understand from the definition, the examples that I provided to you, that utility ranges between 0 and 1.
So it's like, you said between 0 and 1, right?
Yeah.
Because I remember in other courses like infrastructure, we have utility goes to minus.
According to my, yeah, okay, I understand. According to my knowledge, and I will provide you some, also some theoretical foundations for defining utility. According to my knowledge, it ranges between 0 and 1. And, but, you know, it depends on how the other professor defined it. And let me see, I just want to make an inquiry on Wikipedia. In order to find out a reference for what I mean, a reference to be used now. I'm not sure if, let me see. You see, for instance, here, utility is meant as a probability of success, and the probability of success varies between 0 and 1. And, you know, it depends on the definition that the other professor adopted. And according to my definition, and I define utility basing on 3 axioms, and the axioms are those that I'm listing here. So let's suppose that you have alternative decisions, I alternative decision. And let's suppose that you have J criteria to choose among the I alternative decisions. And I would say that, no, sorry, I would say, the 3 axioms for the definition of utility are these. First of all, the utility of let me think how to define it in a clear way, because I have to refer to J's criteria. So let me say utility of the J's criteria. Okay, so the minimum over I of uj is 0. So basically the minimum over the alternative decisions I of the utility for the criteria J is 0, which means that if we refer for J at the economical benefit, and we consider 3 alternative decisions, so I is equal to 3, so I can be equal to 1, 2, and 3, the minimum benefit corresponds to a utility of 0. Basically, a utility of 0 corresponds to the minimum utility across the decision for the criteria J. The second axiom is that maximum over I of utility J is equal to 1. So the maximum of utility is equal to 1. And the third axiom is that the derivative of the utility according to criteria J in the J is not decreasing. So it means that if you refer to the criteria J and let's consider economical benefit, and you see the change, the change in utility for a change in J, change in economical benefit, it cannot decrease, which means that for increasing benefit, I must have a non-decreasing utility. So this is the definition. Basically, the utility is something that varies between 0 and 1, and for increasing value of the considered criteria, I must have a non-decreasing utility. And for instance, one example could be given by a picture like this one. If I consider the economical benefit, and the economical benefit, let's call it NB, like we did before. And I make a picture of utility of NB. Of NB with respect to NB, and NB, which is my economical benefit, can vary between NB min and NB max. And utility varies between 0 and 1. I must start from utility 0 from the minimum benefit. I must get to utility 1 for the maximum benefit. And in between, I must have a non-decreasing progress, which means that I can have a linear variation, for instance, or something like, even something like that. These are just two examples. And of course, the way in which varies between these two extremes depends case by case. The linear change, the linear variation, is probably the most straightforward example that one can give. Like, for instance, if I consider the economical benefit, it's straightforward to rescale the economical benefit between 0 and 1, and you get a scaling that basically doesn't affect your decision, because, I mean, for increasing benefit, I have a corresponding increase in the utility. Instead, if you adopt a nonlinear behavior, what does it mean in this case? It means that if I start from utility 0 to the minimum benefit, I get to utility 1 to a given value of the benefit, NB star. And the situation is such that if I increase my benefit beyond and B star, I don't get any increase of utility, which means that once that I got enough money, if I get more money than that, I don't have any more utility. It could be reasonable. Maybe that it's not reasonable with respect to this example of money, because you may say money is never useless. I would say that it's reasonable also to say that beyond a certain limit it's useless. But let me make another example like water, for instance. If you need water for irrigation, it is, of course, fully justified that once that you got enough water to satisfy your requirements, if you get more water, it's useless. So it is meaningful to say that in this case, if I assign a utility with the amount of water that I receive, it's perfectly reasonable that I get to a maximum of the utility for a certain amount of water, and I don't get any more utility if I exceed this certain amount of water. So the nonlinear change, the nonlinear behavior, the nonlinear pattern is fully justified. And I would say that even for the economical benefit, in some cases, it could be justified. So basically, utility can be defined basing on your problem, on your perception of the benefit that you receive from the alternatives against a specified criteria, and it can be defined in a very flexible way. The only condition that you have to respect are given by these three axioms. Okay, now, I think you can understand what is the usefulness of utility, and keep in mind that utility, even once that you fix the axioms, can be defined in different ways, and we will see that the presence of uncertainty has a strong impact on the definition of utility. So one thing is to define the utility for a net benefit, for instance, that is given for sure by an alternative decision. A completely different story emerges if for each alternative decision you have a net benefit that is uncertain. And then, in the presence of uncertainty, your definition of utility changes. I'm anticipating this because we will see later on next week, on Tuesday, how to define utility in the presence of uncertainty. How one may define utility in the presence of uncertainty. For now, let's assume that, these utility functions with respect to this exercise are defined with certainty, okay? And these utility functions are defined with certainty according to the tables that are given by the text here. So, I need to find it, okay. So basically you see that for the indicator I1, which is economical benefit, we have an utility of 0 for the minimum. Just a second. Okay, perfect. This basically, I have three alternatives. Let me make a summary here. In order to clarify the meaning of these tables, I have three alternatives for the design flow. And the three alternatives, as you know, are given by Q. Let me define the design flow with the symbol Q. Q equal 80 liters per second, Q equal to 100 liters per second, if I'm not wrong, you see, yes, and the Q equal 120 liters per second. And now, let me see what is the shape of the utility function for the net benefit, for the first criteria, utility I1. And here I have Q. So let me use Q as symbol here. Okay, and the table says that for design flow equal to 0, here I have an utility equal to 0, perfect. For the design flow equal to 30, I have a utility that is again equal to 0, which means that if my design flow is lower than 30, I have no utility from the perspective of the economical benefit. And if I have a design flow of 150, I have a utility of 1. So this is the shape of my utility function. And here I have my three alternatives. This is 80, this is 100, and this is 120. So basically you can assess from this table and this graph what is the utility of the three alternatives. So in this case, the utility is not given a value of 0 for the lowest design flow according to the three alternatives. It's given a value of 0 for a design flow of 0 and a value of 0 again for a design flow of 30, which is a slightly different definition with respect to what I introduced there. But the axioms are anyway respected because, of course, in this case, we limit our attention to these three alternatives. But if one extends to all the possible alternatives, then it's clear that my definition is met in this case. And I have similar tables for the other indicators. And look at the different structure. For the indicator I2, what is I2? I2 is the impact on the ecosystem. And therefore, you may easily understand that the impact of this ecosystem is lower if you have a lower design flow, which means that you should give higher utility to low flows and lower utility to high flows. In fact, you see that it starts from a utility 1 for a design flow of 0, which means no plant, which means no impact. And therefore, of course, you get the maximum of the utility in the presence of no impact. And for a value of 150, you get the lowest utility because you have the highest impact. And the same for the landscape, and the same for the tourism. So you have an increasing utility for increasing design flow when you refer to the economical benefit, and you have decreasing utilities for increasing design flow when you refer to the impacts. Okay. Now, I think it is becoming clear what you have to do. For each of the alternative decision, and for each criteria, you have to estimate the utility by using these tables or graphs. Again, for each alternative decision and each criteria. Then, for each decision, you have to combine the utilities for the different criteria by using the weights that you previously estimated. And therefore, for each decision, you will find a resulting utility, like we did for the dam. And then you compare the utility of the three alternative decisions, and you pick up the decision with the highest utility. This is what we should do. What happens? First of all, I think there is a, let me check, there is an R code. Let me modify it. Basically, this R code, first of all, puts into R the utility functions. And you see that each one of these lines is the computation of the utility of, according to criteria 1, U1, for each alternative decision, 80, 100, 120. And then you repeat the same computation for all the criteria up to 4. And then you have for all the decision and all the criteria the resulting utilities. Fine. And then you can compute, you can put together for each decision the utilities according to the 4 criteria in one vector. So basically, you see what I'm doing here is to put in one vector, U80, the 4 utilities. Fine. And then I pass to, and all the utilities are finally included into a matrix. R-bind means row bind, which means by using the vector U80, U100, and U120, create a matrix that is called U. Okay? And this is very easy to make. If I just take these rows and I copy them into R. Let me move to R now. Here. And then I copy them, and then let's look at U. This is the matrix. The utilities according to the criteria 1, 2, 3, 4 of the 3 decisions. Perfect. This is straightforward. It's just an interpolation within these curves, utility curves. Okay, now let me go back to the R code. And then there is this part here, which is the computation of the weights, and we did this already. And in this case, the weights are put into a vector that is called PESI. We had not PESI, but W1 in our R session. We called the vector of the weights, we called it W1. And the weights are different, because you may remember that I changed the matrix, the comparison matrix. Okay, and then I just need to multiply the matrix U times the weights, and then I get the score of each alternative. Let me do that. Of course, I have to change, when I copy, I have to change, I don't have to use PESI, but I have to use W1. And then I just have to sum the rows of this matrix, and these are my utilities. which are very similar, but still I can see that 80 is the preferred solution. They are very similar in this case. And they are similar because of the result of my computation of the weights. So it was not made on purpose, this result. Just the weight that we gave to each criteria that brings me to get similar utilities. Okay, that's it for this exercise. If you don't have any question, given that we have 10 minutes left, I would like to introduce you to the next PowerPoint that I will use on tomorrow, sorry. Which is related to decision under uncertainty. I already told you that this is an extremely important issue. I open it and then I Any question related to the exercise before I start? These 10 minutes discussing this topic. Okay, now let me just remind all of you that what we did so far assumes that the information that we have available to take our decision is not affected by uncertainty. Actually, this is not the case when we work in hydrology and water resources management. I already mentioned to you that these are topics, these are contexts where uncertainty is always present. So in hydrology and water resources management, we are never certain about water availability, water demands. These are all estimates that are taken in the presence of uncertainty at varying degrees. And therefore it is extremely important to account for uncertainty in decision making. This is now recognized as a necessity. I mean, as engineers, we are not only required in water resources management to provide estimates to our stakeholders, but we also have to provide an estimate of uncertainty and its impact. And this is not easy. It's not easy because the presence of uncertainty by itself makes the evaluation of uncertainty affected by uncertainty, which makes the situation a bit complicated because while we are sure that uncertainty is there, we cannot quantify it precisely. Rigorously speaking, this is a quantification that we cannot make. But of course, we can provide an uncertain estimate for uncertainty, which is already a very good contribution. It's already an additional information that we may deliver and that we have to deliver, because it is recognized that the presence of uncertainty affects the decision, and therefore we have to know how the decision is affected. There are several ways to reply to these questions and to address these challenges related to how to decide in the presence of uncertainty. And there are several ways forward because for the very reason that we cannot estimate uncertainty in a precise way. So for the very reason that we provide an estimate of uncertainty that is in turn affected by uncertainty, then we have several alternatives to address this challenge. And some of them are very simple and can be used when the amount of information, additional information that we can provide is limited. I mean, when we are very uncertain in defining uncertainty, and please forgive me for this playing with the words, when we are really uncertain on it, then it's better if we take a simple way forward, because simple methods are usually more robust. And in fact, apart from this introduction, let's suppose that, for instance, I just want to introduce this first method that we will discuss tomorrow. Let's suppose, for instance, that we have a benefit function, which we already considered in this course during the past lectures. I already assumed that for some decision I have to maximize a benefit function. And let me provide this example, for instance, for a benefit function. Let's suppose that x is a water allocation, and the net benefit is reported as with the symbol NB, depending on x, on the ordinate. And this is a case in which the benefit function is defined with certainty. And this function is defined in this way. The analytical form, is this one, which we already considered in the past. You have an income term and a cost term, which penalizes your highest allocation. For increasing allocation, the cost increases, and therefore this function